for a while longer.
Okay, welcome. People are still trickling in. So let's just get started with a couple of opening the floor for questions or anything organizational that's going on. Just like a quick reminder, homework 2 was already posted last Friday. It's due as usual on Friday. And otherwise, there isn't all that much happening this week. Just like if you have any issues with the homeworks, please feel free to use our office hours. You can find them on the schedule. Any questions that you have before we get started with the full lecture? Okay, doesn't sound like it. So let's get started. Today, our plan is to look at a couple of more data structures. Namely, first, we'll look at some built-in Python data structures, tuple set dictionaries. And then mostly, like the most interesting piece of today's lecture will be like looking at Pandas series, because this is the library that we'll be using for data wrangling frequently. But we'll also do like a brief introduction into object-oriented programming and classes. Don't expect that we'll cover classes and objects in depth, but it's more about like how can you use them. We don't really require that you know like program with classes and objects in this class. I do want to recap one thing quickly because I think it's a little bit challenging to wrap one's head around for the first time, and that is list comprehension. So let's get started with this. Remember that list comprehension is this very compact Pythonistic way of modifying or creating lists in Python. And so like this was roughly the syntax. We have the square brackets, so it's kind of the list comprehension. Then we have like a new element here that could also be like an expression. And then we have like a loop for the original element in the original list. And so as I said, a new element can be any expression. You can also refer to original element here in this expression. Original element is just a member of the list, and the list is, of course, the thing that you're using to like base your list comprehension on. And so it's kind of like easier with some examples. So here we have like the here we have a list. This one is not, doesn't use list comprehension. We just created a list based on a range. If we wanted to take that list and replace all of its values with zeros, we could do this. This simply says 0. This is the new element here for like original element in my list. And as I said last time, if you have an original element from the list that you want to don't want to use, you really want mostly an iterator, you use the underscore to signal that. But this is, of course, just any name would be equally valid here. In theory, in practice, this is kind of like the recommended way of doing this. We can also do this to, let's say, create a list with the range function directly. Or and like more interestingly is when you're actually using the original element. So if I'm saying like, basically this here creates a copy of the list, because I'm saying for original elements in my list, make it original element, right? So this is like exactly the same list as my list was. It's just a copy of it. But then it gets more interesting when I start to modify the original element in the list. So for example, if I wanted to take every single value here and multiply it by 2, I could do this with this very short expression here. I can say original element multiplied by 2 for original element in my list. And so now what you see is I have multiplied every single value in this list by 2. And you can do like, you can combine some of the things that we talked about, for example, such as slicing with list comprehension. So for example, here I am taking the list and I'm like like the original my list, I'm multiplying it by 2, but at the same time, I'm also reversing it. So that like what's happening here is that this here reverses my list. By the way, this is also like the simplest solution for one of the homework examples, right? This is like just this reverses a list. And this reverse list is then iterated over and then multiplied by 2, and then I have a list like this. So very, very succinct syntax. Could be a little bit foreign if you're not used to it. You can, of course, also write this with like a regular for loop, but that's going to be much more, let's say, a lot more code. And we've also seen that we can use like proper function calls in like in here. So it doesn't have to be just like an operation. We can, for example, say like len of my list is a function, like a built-in Python function that gives you the length of an data structure. And I'm kind of setting this like len of my list returns 10 for this list. And so every single element in here will be 10. And this was the little bit more interesting example that I showed last time. If random.random gives me a random number in the unit interval, if I want to have like a random number between 0 and 10, I could do something like this. So this would be like a very practical example if I want a list of random numbers with the first like between 0 and 10. Okay, so that is kind of like a quick recap of one of the key things that we talked about last time. Now I want to talk about some additional Python data structures. The first one is actually simple. It's very simple. It's very much like a list, but it's called a tuple. So the only difference between tuples, technically speaking, is that they are immutable. So you can't change a tuple after you've created it, whereas you can change a list. And the typical purpose of tuples is to store objects of different types. Remember that I told you that you should not have a list that has different semantics or different types for each of the members. For a tuple, that is actually okay. That's kind of like what they're made for. And so tuples kind of like have some practical implications for performances and hash table, which we'll discuss later. But now, like, how do you create a tuple? This is like a very simple tuple here. I'm like creating a person with my name, my year of birth, and my kind of like major. And this kind of like it looks a little bit weird, right? Because I'm just saying person and then 3 things next to it. But what happens is this creates this tuple, and we can identify a tuple by the like round parentheses here. So that kind of tells us that this is a tuple and not an array. And so generally, like this is legal, and you'll see why this is legal in a second. But typically, if you want to create a tuple, I would say this is kind of the preferred syntax because it is kind of a little bit more explicit, right? Like you're telling people, I want to create a tuple. So that works just as fine. We can access elements of tuples just like arrays. So if I were to this access index 1, which is the second element in the list, I get like 9081 back. However, as I said, it's immutable, so we cannot change value. So if I try to do this, it will throw a type error. And of course, we can put arbitrary objects into our tuples. So for example, if I have something like a train schedule and I have my train 1, whatever it's called, and it leaves at 7 and 11, I could kind of like put in an array with those 2 numbers. And I can access this simply like I would access a nested array. You see like the train schedule is, it has the tuple outside, but then in here is a regular list. And I can modify the list in here, because when I say it's immutable, this only means it's immutable for kind of like the references, the primitive data type. So if I have a complex data type like an array in a tuple, I can still modify it. So that's something that you have to be a little bit careful about. Immutable doesn't mean that you can't change any of the members. It just means that you can't replace the member with something else. What we could also do is we can nest tuples in tuples, like we can nest lists and lists, right? So here we have like, I'm doing the same thing as up here, but instead of using an array, I'm using a tuple. And in this case, because this is now like this here is immutable and the outside tuple is immutable, this wouldn't work. So this would throw an error. So I'm not going to show it, or well, I can run it. So you'll see that you get a type error. Tuple object does not support item assignment. So yeah. Great. So there's a couple of like, there's nothing special about tuples. They're very much like arrays, but there's a couple of cool things that you can do because of tuples. So let's for example consider this code here. I want to create a function that multiplies 3 values in all possible combinations, like A multiplied by B, A by C, B by C, and A by B and C. And so notice that I'm just returning all of those just separated by commas, right? This is something that is fairly unusual in other programming languages, or in many other programming languages. In another programming language like Java, you would have to create an array and then return that array. In Python, you can do this. This looks like just you're returning now 4 different values. And what's happening behind the scenes here is that you're actually dynamically creating a tuple and you're returning that tuple. So if we run this, we get the result as a tuple. Again, the parentheses give it away. We have the results for all of these different multiplications. So this is also kind of like neat because we can do this shorthand assignment because of this. So we can do something like AB, AC, BC, ABC, and when we call that, this actually works just fine. So this is kind of like if you know exactly what your return type is, you can like call this like that, assign it to variables like this. It's a very efficient way to return multiple values and assign it to some variables. Of course, we don't need a function to do this. We can also just do this kind of like syntax, which is slightly odd, but it's basically like here I'm creating a tuple and here I'm assigning it to those variables. And so you can actually do assignments like this. Okay, any questions about this? By the way, we realized that it's easier for us to handle questions when you type them in the chat on Zoom instead of on Slack. So I think that's going to be the preferred way for everybody to ask questions if you don't want to speak up, because it's just like easier to monitor this little chat window than have like a Slack team with many different channels and so on. Would you be able to modify the values of AB? Yes, but only after you've assigned them. So here, like for example, I am definitely able to modify those values. What I can't do is I couldn't do something like, let's say my tuple, and then I assign this. And now, like if I were to, let's say, print my tuple here. So this is not really a tuple, right? And so I can't modify the tuple in this case. I can't do this. This will throw an error again. But if I assign it to the values like I did here, I can definitely do AB is 19. So this is not going to throw an error. So at that point, I have kind of extracted the value from the tuple, and I'm not actually working with a tuple anymore. Okay, so the next data structure I want to talk about is a set. And like I'm sure you all have a good idea of what a set is, mathematically speaking, and it's very it's like the same thing in programming. It has a couple of interesting properties when you program that are very useful in many cases. So a set is like, in contrast to a tuple, it's mutable, so I can change what is in a set. It is similar to a list, however, it is not ordered, and it cannot contain the same element twice. So like every element in the set is unique. And that's sometimes useful and sometimes tricky. It of course depends on your context, but if you need a set, it is like a great data structure to have. So for example, if I were to, like, sets are initialized with curly brackets. So remember, tuples is parentheses, round brackets, arrays are square brackets, sets are curly brackets. Now I can create a set of my Beatles band members. And so the first thing that you should note here is that, like, the order was John, Paul, Ringo, George, but the output here is a different order. And the order is not, like, you should never assume an order. Like in practice, of course, if you print a set, it will have an order, but you should never make any assumptions about the order of the elements in a set. And this might be a different order depending on your machine, depending on your implementation, depending on your Python version, and so on. So definitely do not try to ever rely on this. So this is one way of initializing a set. And here's another way of initializing a set. I'm just using the set function. And there I could pass in an array. I could equally pass in a tuple. So any kind of like data structure that can be converted. So what's interesting about this example here is that I have passed in John twice. And the set, of course, because it forces that there's only unique values, contains John only once. So if this is what you want, this is, of course, great. So we could, for example, use this to deduplicate a data structure. So maybe it's useful to think a little bit about how this works, because we'll later use this for hash tables. So like the one thing that is cool about sets is that it is very efficient to check whether an element is in a set. So if I have a very, very large set, it is extremely efficient to check whether, let's say, a particular username is in that set of usernames. And the reason why this is efficient is because it uses a data structure that is based on a hash code. And so what happens is that like behind the scenes, there's a function that says that's called probably hash that takes in the string and then computes a mathematical function on it that assigns it kind of like a unique number. And that unique number is then used to index it. So for example, if I wanted to look up, like if I wanted to store Jimmy, I might have a hash function that returns Jimmy like value 16, and John gets value like 145, and Robert gets value 2. And so now these are stored at like in a big array at that particular index. And so when I want to see whether Jimmy actually is in that set, what I don't have to iterate over the array and look at every single element. I just use the hash function, which gives me an index, and then I'm looking up in that set whether there is something at that index. And if there is, then I know like there is this element already exists. If there's nothing stored at that index, then I know this element doesn't exist. And so this is a constant time operation, right? This works just as fast like for like arbitrarily large sets. Like in reality, it's not completely agnostic to the size, of course, because like there might be collisions and so on, but like conceptually, like the hash code, like a hash table or like sets that use hash codes are very efficient to check whether an element is already in there. And so you can make use of this in many different contexts. So is that roughly clear why that works and why this is efficient? So then he's using the in keyword faster than using the key in the in keyword for list. Yes, exactly. If you have a very big list and you have a very big set, basically the checking the in, like using an in keyword for a big set is constant time. It doesn't matter how long the list is. And this is kind of simplified, but more or less that is the way it is. For a list, it depends on how long the list is, because I have to go through every single element and check, are you this, are you this, are you this, are you this, are you this? Whereas for sets, it's just like calculate a mathematical hash function, check if something exists at that particular index. Okay, so we talked about checking existence with the in keyword, and this is how this works. I'm simply saying Jimmy in usernames, and that will return true. And Ringo in usernames would return false because Ringo isn't in our usernames here. This, of course, like you can do the same thing in lists, but as I said just now, this is much slower if you have a very big list. Of course, like a list of 4 elements doesn't make any difference. But for very big lists, it does make a difference. So we can add values to sets by using the add function on a set, just as we've seen in other data structures, and we can remove elements with the remove functions. If a set does not contain a key we want to remove, it will throw a key error. So that is something that you have to be a little bit careful about, because like an error will stop your program from running. So you have to, typically you should either catch an exception, which we haven't really talked about. The easier way to do this is to check whether this actually exists. So this would be the safe syntax. So if Joseph in usernames, then remove it, but otherwise don't. So this of course doesn't exist, doesn't execute, like this line here doesn't execute because this here returns false. We can iterate over the values of a set, but of course remember that you don't should make any assumptions about the order. But still, this can be useful in many cases. I can do for a name and usernames. I can iterate over the elements in a set just like for a list. Okay, so I linked to the documentation. There's more stuff that you can do with sets. And now I want to move on to kind of like the set's big brother, which is the dictionary. And a dictionary is basically, it's a set that also stores an additional value for each of the elements in the set. So what you have in a dictionary is you have key value pairs. So there's the question by Jeffrey is there a purpose of the names not coming out in a specific order? The purpose is that the way this works with the hash function, so behind the scenes, the hash function doesn't give you an order. And so storing an order would be like additional overhead. And in a set, you typically, that's kind of like if you want order, then you need a list. But if you want fast checks and making sure that elements are unique, then this is a set. And so the reason behind it is like implementation and kind of like the pros and cons of the different data structures. You will see that Pandas series can actually do both. So Pandas series are kind of like this more complicated, fancy data structure that do kind of like set-based and hash-based access in addition to order and also allow duplicates. So, but these are like the basic data structures. And so they're kind of like kept simple, but usually it's not a problem, right? Like if you want order, you just use a list. If you don't want order, you can use a set. Okay, so dictionaries, key value pairs. So the keys are kind of like the values in our set, and the value here is the payload. These dictionaries are like often also called associative arrays or hash maps. That's kind of like the word that I kind of like learned the most, or hash tables. So these are all the same things. Python does call them dictionaries. And you see that dictionaries are initialized with curly brackets. And so that shows their relationship to the sets already. And then the difference to sets is that we now don't just have like a key, but we have a key value pair. And so here I'm taking a couple of musicians and their bands, like John is Zeppelin, Jimmy is Zeppelin, Paul is Beatles, Ringo is Beatles. And so the properties of set hold, you can have keys have to be unique. And of course, they're still not, dictionaries are also not ordered, but our values can be whatever we want. So it's totally fair game to have like two people here that are in Zeppelin. Yeah, and so the colon sign here is kind of like what separates the key from the value. There's of course other ways of creating a dictionary, like we had for sets. I can use the dict keyword and then pass in, let's say, an array of tuples. So here I'm having Tom York and Dave Grohl for Radiohead and the Foo Fighters, and that will result in a dictionary just as well. A dictionary, a key can be of any data type, but in practice, it should be like the dictionary can generally be of any data type. So I can do this, like here I did it with strings, but I couldn't do this with numbers. But typically, like in Python, a hash function is defined on every single data type, but typically you do not want to use floating points numbers for keys in hash tables because of the problem with like floating point values never being exactly the same, right? So like if you have like 1.00000 something, the next time you have that, it might not be exactly the same, and that's why you shouldn't, like why you can't check two floats whether they're the same with equality signs, and that's why you should also never use a floating point number as the key in a hash function. So here I'm using integers. It's totally fine to use floating point numbers as the values in a hash function. So like in practice, I would recommend that your keys in a hash, in a dictionary should either be integers or strings. These are the two data types that really like work reliably. It can be anything, but those two are kind of like the what you should really stick to. But values can be complex data types. So they can be lists, they can be floats, they can be strings, or they can be generic objects. So here, for example, I have a couple of musicians that have been in multiple bands over their careers. And so I kind of want to like store that in my dictionary here. And so I'm saying Dave is like, and then I'm passing in an array, and that is like Nirvana and Foo Fighters. And then I have Eric, who is part of the Yardbirds, Cream, and also a solo artist. And so just to show that I can use like this complex data structure as a value here for a dictionary. Dictionary elements are accessed just as elements in a list with square brackets, but instead of the index, we pass in the key. So if I have numbers, I like, this is the array here, I get back the value, or this is the dictionary here, I get back the value 1.45. If I pass in Eric into multi-band musicians, I get back an array that contains those three like bands or his solo band. We can add elements to a dictionary by simply saying musicians Tom is Radiohead. So here, like this key doesn't exist before that, but after I've done this, this will just work fine. And I can remove them using the delete keyword as we did for sets. But again, we have to worry about key error. So if we try to remove Tom again, we would get a key error. And so we would have to do something similar as we did before. Check if Tom is in musicians, then remove it. Otherwise, don't do anything. We then can access a list of keys and values separately. So for example, I can ask for all of the keys of the musicians. And notice that this isn't really like what you get back here is not just like a simple array, but it is like this complicated object that's called a view object. I've linked some details here. What that means is that, like in practice, why you care is that this view object is updated once the list changes. So for example, if you assign like my keys is musicians.keys, and if I update the musicians later, my keys will also be updated. So those are kind of like linked to each other. This isn't just like a simple array, but it's a view object that gives you a view on that dictionary. And this is kind of useful because like, even though they're not ordered, it's often useful to iterate over a data structure like this, because maybe I want to manipulate every single one, or I want to print them or something like that. And I can do something like for musicians in musicians.keys. And then I can print all of the keys here. I similarly can do this for values. So here, if I do that for values, I get all of the values, but I don't have the keys. And I can do this for items. And items returns a tuple with key value pairs. And so like that's a useful way to iterate over such a dictionary. For example, like we can use this kind of like syntax that I said that I introduced earlier with tuples to kind of like assign those two values here dynamically, because musicians.items returns a tuple. So I can do for key value in musicians.items, I can print key and value pairs like this, for example, or use them in any other way that I want to. So that's kind of like, this is kind of the way, if you ever want to iterate over the key value pairs in a dictionary, this is the way to do it. You can also do this, which is like, here I'm just saying for k in musicians.keys, and then just like print the key and then retrieve the value by using this access function. This is slightly less fast, but it probably doesn't matter all that much. So this is the kind of like the more elegant way, which uses a slightly unusual syntax. This works just as well, maybe like a little bit slower, but by mostly a constant factor. So don't worry about it too much. Okay, so these were kind of like the basic Python data structures that I wanted to cover. Do we have any questions about dictionaries?
Can you index, like instead of using the key, can you still use the index to refer to like location in the dictionary?
No, you cannot use an index of a dictionary because you don't even know what the index is, right? So that index is a hash, like a hash value, and so you can't do that. And it's actually not inefficient to access it by the key. It's actually very efficient, like about as if not quite as efficient as an index, but about as efficient. Okay. So I'll briefly introduce classes and objects, and then we'll do our short break. So like I'm sure many of you have heard about object-oriented programming. I'm just going to say we're not going to use object-oriented programming much in this class. Like we're not going to write classes or complex programs that have like where you create your own classes and so on. But we will very, very frequently use objects that libraries return to us. So I just wanted to give you a little bit of a sense of like what object-oriented programming is, though like there's a lot of nuance to it, and there's like lots of like more advanced cases. What I really like want to take you to take away is like how do I actually use objects that are returned by libraries, and understand a little bit about what's going on. But I don't need you to like be able to like write complex programs with object-oriented programming paradigms. So the idea of object is that like we've seen a lot of data structures like lists and tuples and dictionaries that have like a very like say rigid structure, right? They have like either just values or key value pairs. Objects are arbitrarily complex. So I can have like, let's say an object that's called a person, and there I can store a name, I can store an age, a birth year, a nationality, a list of all of their preferred kind of like hobbies, and I can add methods and functions to manipulate that object. So I could say, like say I'm picking up a new hobby, I could have like an add hobby function that adds a new hobby to my object. So objects are really kind of like this extension of this idea of data structures into arbitrary complexity. So I can have like whatever I want in an object and all of the methods and functions in place to operate on it. And that's kind of like the basic idea of object-oriented programming. And so like we are mixing data and functions that go together in an object. And these functions are like if they're part of an object or part of a class, we usually call these function methods. So they're the same thing. It's just a distinction that the method is defined on an object and not just like a general purpose function. And so like objects are like as I said are these great data structure, and objects you have to kind of like at some point you have to specify how an object looks, right? Like what are the legal values, what are the different functionalities that an object provides, and that's what classes are. And so you can think of an object as like a concrete instance, like if let's suppose we have a class human being, or like class person, and then we have an instance Alex, right? Like I am a human, I have certain properties, but I can also like write a class that describes properties of humans more generally, right? And I can have all of these functions associated with it. And so this is exactly what we're doing here. We're saying there's a class person, and then we can assign variables to a class. We can then set methods setting the value of a member. So here, for example, I could do set name, and then like I'll have this like interesting variable here, self and name. So this is kind of like a little bit of a syntactical weirdness of Python. Self here is a reference to a particular instance of that class person. So if I wanted to store, like I'm using the set name function later, if I wanted to store the value name here, what I have to do is I have to call self.name equals name. And this way, Python knows that what you want to do is you want to store that parameter here into that class member that you have defined up here. You can also, for example, like have a method that just prints something. It doesn't have to, like, it doesn't have to take a variable. I still have to have myself here, but I'm not actually using the self when I call this this method. So here I'm like, if I wanted to print my name, I would do this. Okay, so let's review this quickly based on what I've written here. So class is kind of the keyword that tells us we want to create this new template for objects. And then we have like member variables, and then we have methods that operate either on as member variables or do something else. By the way, self here, again, this is the convention that it's supposed to be called self, but it doesn't have to be called self, but you should call it self. But what is important is that it's the first parameter. The order here is what counts. And interestingly, and this is slightly weird about Python, and this isn't quite the case in other programming languages, is that now, like the self here, I have to explicitly write it in my function, but I don't use it in when I use the object or the class. So like here, I am kind of like creating a new object of type person, and I'm assigning that to the variable Ringo. I have nothing, like this is still empty, so we have nothing in that person Ringo at this point. And so if I were to call Ringo.printName, the first response here will be blank because this is what I initialized it with here. Now I can do Ringo.setName and set his name to be Ringo. And as you can see, like the setName function in the setName method here has both the self and a name. But as I said earlier, the self isn't like, that's only for use within the class. So you kind of ignore that outside, like when you use it, and you're just starting with like the second parameter. And then after I have I have set the name and I call print name again. Again, here I don't have, like, there's a self, of course, but I'm not using it. And so if I do that, it will print the name. And then I can also directly access like member variables of an object. So here I'm calling methods, but here I'm actually accessing a class member and returning it. And so I see the output here of Ringo. So like, yeah, if we execute this, we see that like we first have a blank name, then we have the name Ringo, and the return value of this cell here is Ringo, which I have done through direct member access. The key point here is this dot notation, because we will be using this a lot, right? I have object.method or object.name. So this is kind of like how I access things that are part of an object. So yeah, I think this is a good time to take our 5-minute break. We'll come back at 1:07, and then we'll look at a little bit more complicated objects. Okay, let's continue. So yeah, we've created our own class. We have we've created an object based on this class. So this, which is also called instantiating a class. And now we can we've done this only once, but I can, of course, this is a class, right? So I can reuse it and I can create a different person based on that class. And so here I'm creating Paul, and I'm saying Paul is also a person, and I'm setting Paul.set name Paul. And if I print Paul's name, that will work. And of course, at the same time, I also have Ringo, and I can print Ringo's name. So as you can see, I have kind of like these kind of like, well, advanced. This is not a very complex object, but I have these objects that store the value and that have these kinds of methods that do something with it, like printing the name. The interesting thing is, if we ask for the data type of a Ringo variable, we can see that it's actually an instance of our class. So kind of like, think of it like we have data types like integers and strings and so on, but now we have the ability to create our own data types that have exactly the things that we need. And so you can see Ringo is of data type person. And like behind the scenes, for example, something like string is implemented just like this. So one thing that I've done here is like I've always created Paul as this empty person, but you could say, or Ringo, I've always created persons emptily, but you could say that some things like some variables are so important to an object, to a class, that I always need to have them, right? So for example, if I wanted to always require that a person has a name, I couldn't really enforce that, right? Because I can choose to call set name or not. So it doesn't, like, nothing forces me to specify a name. And so the way to force people to specify properties is with this special init method. And this init method is typically, like, generically, this is called a constructor. And so constructor is a method that takes a couple of variables that is responsible for setting up an object, and that kind of stores the main, or that initializes the object in any way. And that's why init is kind of like a useful name. In contrast to, like, for example, the self up there, here the actual name with those two underscores here matters. So it has to be exactly underscore underscore init underscore underscore. That is necessary. And then I have to have myself, and then any additional parameters here are optional. So I can specify what parameters these are. And so let's say I want to have like a class musician, and a musician has a name and an instrument. And I want to force everybody who creates a musician to specify both the name and the instrument. So if I don't have those two things, I just don't want to be able to create an object like this. And I can do this with this init function. So here, down here, you see how I then call it. I say Ringo equals musician, or is musician. And then I have those two parameters, the name and his instrument. So let's look at how this works behind the scenes. We have we assign like these variables here, self.name equals name. Notice that I don't have like this as a class variable outside, but I can just do this in the constructor here. And then self.instrument is instrument. And so here now I'm kind of like telling this class, those are now members of your class, and you always, when you create them, take those two parameters and then store them forever with the names. And then I can do things like print musicians, and here I can use these names. I can say like name plays instrument. And if I execute this down here, I have to run this cell, then it's not going to work. But if I execute this cell here, I have Ringo plays drums. So this is similar to like a setter as I had it up here, set name, with the big difference. I can't create, like, I can't do this. So this will throw an error. So I have to actually specify those two parameters for this object to be created. Again, we can access these members directly, just as we did before. Yeah, and I just showed this already, so this will fail. if you want to kind of like make it easy for people to instantiate an object with like a name and an instrument, you can use default values. So you could say something like class musician init, and then I can like we did for functions. We can also do this for the init method here. How does Python know name is a string? Because of its data type. So Python isn't really like, remember that Python is dynamically typed. So it just infers the type basically from like whatever you pass in. Then Chad is asking, init allows passing of a parameter when creating an object, and class variables are always going to be the value set in the class. I'm not completely sure I understand this correctly, but yes, init allows me to pass parameters that I can use to initialize class variables, but nothing forces me to do that later then. Yeah, this is Paul, this is gonna work, right? This is like, it's not actually, this is then not storing it as a string. This is just gonna show musician 1, 2. So this is gonna store it as an integer. That's why it's dynamically typed. So if you wanted to make clear that you want a string, you could use type hints, but there's no way in Python to make this illegal that you pass into integers. So yes, so first in it I can use this, what I pass in here, right? But I don't have to use it. So if I remove this line here, name isn't actually used. I can just print my name, or I can use it for something else in my init. But it's like very common to use the things that you pass on here as kind of like member variables, but it's definitely not necessary. Sometimes maybe you want to have a random seed or something like that that you use to create a value. And I like, if I don't do this here, like if I like, this is not like, for example, if I have a musician class like this and I create this, and then I try poll.name, this isn't gonna work. So you can see attribute error, musician object has no attribute name. So I have to like actually say self.name is name here, and then this line is gonna work. Andreas, does it make sense?
Yes, thanks.
Okay, and then JC is asking, what are the default values? What does it mean to be a default value? So I can like, in Python and all kinds of functions, sometimes it's useful to have default values for parameters. Like usually you don't assume that you have a default value, but sometimes it makes sense, right? And so like in any other function in the constructor, I can pass in a default name if I want to. And so now, like now this is legal to do. I can still put in here like Paul as a string. And this is going to work, right? But now I'm not forced to do it. I can, but because I have default values, I'm not forced to. JC, does this answer your question? Okay. Then Bernard is asking, if you want to access an object variables in its function, do you have to specify self as one of the parameters in the function? Yes, you have to, and you also have to use the self dot notation. So this is not necessary. Okay, so quick introduction. There's like more nuance to object-oriented programming. For example, I could say, so it's sometimes it's just convenient. Like forcing is one part of the function, one part of the property. But for example, if I want to initialize a complex object, I might like not want to have 5 lines with like set this, set that, set this, set that. But instead, let's say instrument is, I could also have backup, singer is false, right? And so this makes sense to just say Paul plays guitar, but then I don't want to necessarily, like, backup singer is very common, right? So I don't want to necessarily have to specify it. And then it's just like convenient. it's and like a convenient way to initialize it. If I didn't do this, I would have to have a set backup singer property and so on. So it just makes it a little bit longer and a little bit more annoying to write. Okay, so one thing that I, for example, didn't cover, I could have like musician inherit the properties of a person. This is something that you do frequently in object-oriented programming. Like a musician is a person, so you could kind of like inherit properties from other objects. But this is getting a little bit complex, and so this isn't really the point of our class here. But just so this is like how you create basic objects. Most important is that you understand that an object is a complex data structure that is based on a class. An object has member variables, and you can call functions on an object. And if you want to like do proper object-oriented programming, there's like a couple of other classes that that teach you how to do this in detail. Great. There's no private and public in Python as far as I'm aware. So like the whole, yeah, as you can see, I can also directly access a variable, a member variable directly without having to specify it whether it's private or public. So this is kind of like the big difference between a language like Java, which tries to be very secure and controlled and safe, and Python, which emphasizes ease of use and ease of readability and kind of like misses a lot of the complexity therefore. Okay. So we talked about modules before, but I kind of wanted to quickly recap them here because they're very related to classes. And so like modules are essentially like Python files. And in those modules, you can have like functionality that you can then import into another Python program and then use it. And so we've used this before. We've said import math, and then we could use this math.square root notation like we did as if math were a class and square root were a method. We can also use this kind of like it's a couple of different notations that are useful sometimes. So I can say, from the math package, import the log10 function. And so now I can use log10 here without doing math dot. So I could, like this is going to work just fine. And similarly, what I can also do is from math import star. And star is usually in like lots of contexts is kind of a qualifier for everything possible. And in this case here, it means from math import all the functions directly into my namespace. And now log2 here would be defined, but this is generally strongly discouraged, right? Because you might have your own log2 function defined, and then you would have a name clash. And so generally, like this is bad practice. So you either want to have like math and access it with the dot notation, or you want to do some, if you want to use like one function all like very much, this is totally fine, but you shouldn't typically use this. Import star is the same as import math. No, import star isn't specified, right? Like that is just, there's hundreds of packages out there. So you have to say from math import everything like star. You can't just say import star. If you say import math, then you have to use the math dot syntax. And then another thing that we've already done before, but haven't really talked about, is we can redefine the names of modules. So for example, if we're type lazy and we don't want to say math.square root, we can say import math as m. And m.square root is like slightly shorter, and that makes it easier to type. So we will, like, this is something that is super common. So for example, if we import pandas, we will usually do this as PD because we will be calling like a lot PD dot something. And so this is very, very common. And at the same time, you also don't want to have like PD is not a good name, right? So like packages themselves need to have longer names, but then you can use them as shorthand in your own program. And so that's a very convenient way to create these shorthands. And so, yeah, as you can see, this works just fine. Great. So this is just like a formally introducing some stuff that we've already used, and so that you like know what is going on if you see any of those statements. Great. So I want to get to the last part of today's lecture, which is starting to introduce the Pandas library. And the Pandas library is this like amazing data wrangling library, which is kind of like based on the idea of R data frames. So if you're familiar with R data frames, you will recognize some of those things in here. And Pandas comes originally from like time series analysis, but now like it's really good for time series analysis, but you can use it for any kind of tablet data. And Pandas provides 3 different data structures, a series, a data frame, and a panel. The series is like a single column or like a vector or a single list. It's a little bit fancier than a simple list. We'll see what the difference is. A data frame is kind of like, you can think of it as like a big table or a matrix or anything like that. John is asking, if we import into a class, do we have to import before creating an instance of the class? I'm like not completely sure, but I'm expecting that no, you don't. Like if you import within a class, 99.9% sure that like you don't have to explicitly import because you don't actually know what the class contains. Also, modules can import other stuff that you don't know about. It's not necessarily going to be exposed to you in the same namespace afterwards. Okay, so back to series. So we have series, which is like a single column essentially in a table, a data frame that is essentially a table, and a panel that is multiple data frames that like it's basically a 3-dimensional table in that sense. We'll be mostly like dealing with series and data frames, and today we'll be like just introducing series, and then we'll do the more generic data frame on Thursday. If you haven't, if like Pandas is very likely already installed with your Conda installation, but if it is not, this is something that you could. Panels are deprecated. I actually don't know. I rarely use them, so very likely that they're deprecated, and I haven't been aware of it because I don't use them anyway. So they don't really make a ton of sense. So if you don't have Pandas installed, you can run this command on your command line interface, and this should be installing it. This is like installing it via Condas, and sometimes we also give instructions via pip. Pip is the Python package manager. Conda is just like the framework. So the 2 different, like generally, if you can install something via Conda, you should probably install it via Conda, but installing it via pip is fine too. And now we're importing the Pandas package, and I'm redefining this as PD, as I mentioned earlier when I talked about modules. So this is kind of like the standard way of doing this. Okay, so now let's look at as our first series. They're the like most fundamental data structure, and they look a lot like an array. So I'm creating a series with pd.series, and then I'm passing into like into this function, I'm passing in an array of values. And now I can look at the output. What I see here is, well, it looks like, well, I have a list of those elements, but it doesn't look like a regular Python list, right? So first it has explicit indices here. It shows 1, 0, 1, 2, 3. In an array, those are kind of like implicit. Then it tells me about the data type. So we can tell this isn't like our standard Python data structure anymore. The data type here is object, which in kind of like Pandas speak means it can be anything, including a string. And so you have either object or integers or floats in here, or time or some other types. But anyways, I can do the same thing like with integers, like here. And now you can see that the data type here is int64. And the int64 already hints at what's going on behind the scenes. This isn't a Python integer anymore, but this is like a C integer with a specific length of 64 bits. So we have like things like overflows can be an issue, just so you're aware of it. So like the results here, like they in this these are kind of objects, and we can see an index like this column here more or less, which is in Pandas speak also often called an axis. And by default, this is an integer sequence starting at 0, as you would an array, but it can be anything. So that's kind of like the way well, I'll show this a little bit later. And then we have our values that are kind of like the payload of what we had here. And so we have key value pairs, and these keys, they can be implicit, like the index here. So that tells you it works like a list, but these keys can also be something specific. Like I could say, put in a string here. And so the series can work both like a dictionary and like an array at the same time. We can also use other data types as indices, as I mentioned. So for example, here, I'm creating a series that has the values of these years. And then the index are band names. These years are the founding years of these different bands. And the index here is kind of like more or less is the key in a dictionary. And then I can also name my series here. And if I run this, I get like as a return value, I get like index is stones value, or key is stones value is 1962. Keys Beatles value is 1960. Keys Zeppelin value is 1968. And now here's the curious bit. We have two Pink Floyds. Pink Floyd was like refounded in 2012. They had like a hiatus. And so I put this value in here twice. And that is now like I have a key value pair like a dictionary, but I can have two keys of the same type. That's kind of unique about series. That's how it's different from like a typical dictionary. In practice, this is still challenging to work with, but I'll show you some examples why. But it is possible in a Pandas series. So we can access the values like this with bands.values, and you can see like I get back an array. You can also see I get back a view object of the array. So this is similar to like this is going to change if the bands changes. We can look at how the index is composed. So if we have bands.index, remember bands, we had the index was automatically generated. We didn't specify it. And so if I look at the bands.index, it tells us it's a range index. So this isn't actually an array of keys or anything like that. It's just a rule. Like it starts at 4, it starts at 0, stops at 4, and it has step 1. But if we have, let's say, an index where we have actual band names, then we'll see a list of these indices in here. So this is the same call, very different responses depending on how it's constructed. We can access individual entries as we would have accessed them in an array or a dictionary with like a square brackets notation. And that works like just as well for complex keys. And there's also like a get method that does more or less the same thing. And these access methods are as fast as a dictionary lookup, roughly, and they're much faster than a lookup in a list. So this is kind of like a cool feature of series that they combine the best of both lists and dictionaries. One thing that doesn't work in most or in Python native data structures is I cannot just get a list of items based on a list. So in a Pandas series, I can say bands founded get and then pass in a list of keys, and then I'll get back another series that contains only those elements. So that's kind of like a very neat thing that we'll be using a lot, kind of a way to filter out like the values from a series that we care about by passing in like a subset of the keys. We don't get like a simple data type here. Like notice that if I call get here, I get like a simple data type. This is just an integer. But if I use get with this, my return type is a series. So it shows us that the series is a little bit tricky. That depend like for the same functions, I can get values of different types. So I have to kind of like know what I'm expecting to be able to deal with it properly. So there's also like these special indexers for label-based access. And this is gonna like this is gonna sound confusing now, but it's gonna make more sense when we talk about like tables, two-dimensional data structures. For one-dimensional data structures like a series, it's kind of like redundant. I can do bands founded.log of stones, which is does just the same. This is equivalent to this down here. Similarly, I can do the iLog. This is the index location. And so this now, like bands founded, remember, is based on string keys, but now like a series is also ordered, unlike a set or a hash table. I can actually retrieve the element at index 1. So this works. I get back 1960. There's also another indexer which is deprecated and which shouldn't be used. So like you might be wondering, like what's the point of having lock and the square bracket access? But in the answer is in series there isn't really much, but in when we have a table, we will see that the square brackets operate on the columns and the log operates on the rows. And so that's gonna be like the big difference. If I use square brackets, I can retrieve the columns of a table. If I use log, I can retrieve the rows of a table. And if I combine both of them, I can get, of course, like a slice of a data set. For iterating, this works just as you would expect. I can say for band in bands, print band. I can also do this key value thing by using the items functions as we have in a dictionary. So I can say for band founded in bands founded.items. This works just as with a dictionary. We can also update things as we would expect. However, you have to be a little bit careful if you're updating a series with duplicate indices. So for example, like, well, let me first show this. Like I'm updating here based on, like I can add a new item directly by assigning it to a new index. And also notice that the indices don't have to be sequential. This is something that's kind of weird, right? Because like this, yeah, I can just say bands of 17 is the who. So this is kind of like where this, it's both a dictionary and a list shows. The thing that you have to be careful about is that if we update based on an index that occurs more than once, all of the instances are updated. So remember that we have Pink Floyd, which was founded twice in 1965 and 2012. And if I do this here, then both of those instances will be updated. So we now see Pink Floyd has 2015 for both of those values. So if I wanted to use, like, if I wanted to update only one of them, I would have to use the iLog indexer. But in practice, of course, this is something that is weird. So you might not want to do this, but it does work. So I can change this back to like 1965 here, and I can see now that those two are different. Typically, I don't delete stuff from data frames. It's rare. I usually create a slice or I filter it, and then I create a copy of a data frame, but I can delete it. And I can delete something with the delete keyword as we have here. Let me see how far, we have like 10 minutes left. Yeah, I'll keep going. And the exercise for today, it's another activity. It has some of these things. They're testing it. I'm sorry that we're not getting to the exercise in lecture time today, but if you're busy, remember we already have 3 completed exercises and we're only in lecture 5, and you have at most 5 activities. So if you miss one, it's not a big deal. So I'm sorry for this being a little bit much today. Okay. Now I want to talk about indexing and slicing. And this works largely like normal Python, but instead of just directly using the bracket notation, it is typically recommended to use iLog for indexing by position and log for indexing by label indices. And so here I have bands founded iLog 1, 2, 3, and this gives me exactly what I would expected. I'm starting at index 1 and then I'm ending at index 2. Index 3 here isn't included. But if I am slicing by labeled index, that last value is included. So here 3 isn't included, but if I do this, sample into Pink Floyd actually is included. Sounds a little bit weird, but if you think about it, it does make sense because it's not position based, right? It's more like a dictionary. It's just like one of those things that you have to be aware of, that it doesn't trip you up. So here, like if you're using log, you're actually like, you're typically not thinking so much about like the indices, but rather you're thinking more about like what are the names. And similarly, if you like, this gets a little bit tricky here. It looks like because I'm using log, it looks like I'm actually using it by number, but I'm actually using it by the index label. And so 17 here is included, right? So ilog wouldn't actually work with 17, but if I did ilog 1 to 2, then I would get just one value because it doesn't include that 2 value. But if I use log to 17, I get all of those things. Again, for series, but not for data frames, log and just using bracket notation is identical, so I can do this. And another cool thing is that I can use both ilog and log with arrays, which I can't do in vanilla Python. So this is kind of like a neat thing. And as I said, we'll be using this in a second. And this can also be used with Boolean arrays. So here, let's look at this bands founded series again. And now I'm passing in a Boolean array, like true, false, false, true. So I kind of like, what I'm trying to say is I want the first, but not the second, not the third, and then again the fourth value. And that's a way to filter this series. So you can see now I have the Beatles and the second Pink Floyd entry left. And that doesn't sound like, it doesn't seem super cool by itself, but it is super cool once you like know the next thing here, masking and filtering, because then of course we computationally want to create these Boolean arrays. So how does that work? We can create these Boolean arrays with like a method that's called broadcasting. So we can say, like, we can create a mask, and we can say the mask is bands founded larger than 1964. And so what you see now is I get back another series that looks for this expression. And whenever this is true, it puts in true in the series. And whenever this is false, it puts in false in the series. And so that kind of like already hints at what I can do now, right? I can say bands founded larger than 1964. That returns a Boolean value array. Up here, I said I can filter based on a Boolean array. And so basically what I'm saying is I can filter based on an expression like this. So I can do, if I use 0, 1 instead of false or true, these are actually like not, I'm not specifying the, this, if I use 0 and 1s here, that would not work, because then it would expect these are indices, right? It wouldn't expect those to be ordered lists of Boolean values. I can like pass in an array of indices. So here is like this technique here of like taking like a series and then applying an operation to it. That's called broadcasting. And so I can say, for example, the bands are founded in a particular year. If I wanted to convert this to month, I could just say bands founded multiplied by 12. And it's not particularly useful here, but you can see that I actually have applied an operation on a whole array without ever running a for loop or even list comprehension, right? I just said, here's my series, multiply the whole series by 12, and it does what I was trying to do. And so the cool part now is, I can use this for filtering. So remember, the mask here has false, true, true, true. And now I have my bands founded array. And if I apply that mask, you can see that I now have like filtered out the first row, the Beatles that had the word like that was founded before 1964. So now I have kind of like subsetted my series in this new series that I've created. And of course, I don't have to store this intermediate result in a mask here. I can just say bands founded, square brackets, bands founded of larger than 1967. And that does the same thing. Well, in this case, I changed the expression from 1964 to 67. So the result is slightly different. But that's kind of like a simple way to filter a series. So I'm sure this is kind of like a little bit something to get used to, but it is very, very handy to kind of like wrangle data sets. Series like NumPy arrays and like data frames do have a lot of things that we can like run on them. For example, we can calculate all kinds of statistical properties on them. So we can like first I can count them, right? How many elements are there? The none values here are not counted. So if I now have not a number values, they are not counted in this particular count function. Does that make a copy or change the original? Everything that you do like with broadcasting and so on makes a copy. So the original is not changed. If you wanted to store that, you would have to like assign it to that same variable. So statistical other statistical functions that you can call like run is sum or mean or median. If you just want to get like an overview of what's going on with a series, you can say series.describe, and it gives you like all of these kind of like simple statistical properties like the count, the mean, the standard deviation, the min, 25% quartile, and so on, and the max values and all of that stuff. I can also like not a number or non-values are ignored here. One thing that we have to often deal with not a number values, we can kind of like try to impute them, or we can just remove them. The simple way is to remove them. And so if I call the drop an a value, like I'm now getting rid of my not a number value here. And now I can work with this like in a more, let's say, sensible manner. If I were to run this on a series that doesn't contain numbers, I of course don't get averages, but I get kind of like description of these categorical values. I have 6 different elements, 6 of them are unique. The top here isn't of course all that important because they're all unique. And then the frequency of 1 for the top one. Other methods are asking for a specific quantile, the minimum, the maximum, and so on. Okay, so there's still like a couple of other things, but we are at time. So I'll just like do this at the beginning of the next lecture. I do encourage you to take a look at the exercise. It just recaps the stuff that we did today. It shouldn't take you all that long. I can set up breakout rooms, but I don't necessarily expect you, and I'll leave the breakout rooms open for 20 minutes, but we don't necessarily expect you to be in them. So if you don't want to be in a breakout room, maybe sign off in the next 2 minutes. But if you want to be in a breakout room and work with somebody on the exercise, then just stay on.